Hi, my name is Sharon, and today I'll be presenting my assignment, which is the design and analysis of an air conditioning system for a tropical climate building. And this project focuses on the thermodynamic analysis of an air handling unit, or we call it as AHU, operating under tropical climate conditions using psychrometric analysis. And the main objective is to evaluate how the air conditioning system cools and dehumidifies outdoor air before supplying into an indoor space. In addition, I will compare two different operating strategies. So first is a 100% fresh air system where all the supply air comes directly from outside. And the second one is a mixed air system where outdoor air is mixed with conditioned return air before entering the cooling coil. So by comparing these two systems, we can determine which design provide better energy efficiency while still remaining the indoor thermal comfort. And this slide also introduced the design condition used throughout the analysis. So why do I choose this condition is because that Malaysia has a tropical climate with temperatures commonly ranging between 28 and 37 degrees Celsius and relative humidity between 70 and 90%. And because of this hot and humid environment, HVAC system must remove not only heat but also a significant amount of moisture from the air. So the outdoor design condition selected for this project is 35 degrees Celsius with 80% of relative humidity. This represents a typical hot afternoon in Malaysia. And the target indoor comfort condition is 25 degrees Celsius with 50% relative humidity. These values are based on ASHRAE thermal comfort recommendation, which provide a comfortable indoor environment while controlling humidity. And the total supply airflow rate is 120 cubic meters per minute. So using these design conditions, psychrometric analysis is performed to determine the air properties and evaluate the performance of AHU. And this slide presents the psychrometric analysis of the outdoor air. So using the psychrometric chart, the outdoor air condition is selected at the intersection of 35 degrees Celsius of dry bulb temperature and 80% of relative humidity. And from this point, several important thermodynamic properties can be obtained. So the humidity ratio is 0.02 at 9 kilograms of water per kilogram of dry air. The enthalpy is 109.27 kilojoules per kilogram. The dew point temperature is approximately 31 degrees Celsius, while the wet bulb temperature is approximately 31.8 degrees Celsius. These properties help us to understand the condition of the outdoor air before it enters the air conditioning system. The humidity ratios show that the outdoor air contains a very large amount of moisture. The high enthalpy indicates that the air contains a considerable amount of thermal energy, meaning that the cooling coil must remove both sensible and latent heat. And another important property is the dew point temperature. Since condensation only occurs when the air is cooled below the dew point, the cooling coil must operate below 31 degrees Celsius to remove moisture effectively. Therefore, this psychrometric analysis provides the thermodynamic foundation for the entire HVAC system. So after analyzing the outdoor air, the next step is selecting the intermediate step at the cooling coil outlet. So for this project, I selected 15 degrees Celsius saturated air, which means that the relative humidity is 100%. The humidity ratio at this condition is 0.01065 kilograms per kilogram, and the enthalpy is 42 kilojoules per kilogram. And there's three main reasons that I'm selecting for this condition. First, the temperature is well below the outdoor dew point of approximately 31 degrees Celsius, and this allows water vapor to condense a cooling coil surface and reducing the humidity ratio by approximately 61.3%. Second, the selected temperature remains safely above the freezing point, and this prevents ice formation on the cooling coil, ensuring that stable airflow and reliable operation of the AHU. Third, the selected condition provides an effective balance between cooling performance and energy efficiency. The enthalpy decreases significantly from approximately 109 kilojoules per kilogram to 42 kilojoules per kilogram, meaning a large amount of thermal energy has been removed without excessive cooling. Therefore, this intermediate state is suitable for tropical HVAC applications. This slide shows the result for 100% fresh air system. In this configuration, all outdoor air passes directly through the cooling coil before being reheated and supplied to the room. Since the outdoor air has a high temperature and humidity, the cooling coil performs both sensible cooling and latent cooling. The system removes approximately 2.56 kg of moisture every minute, and this means that water vapors continuously condenses on the cooling coil during operations. The calculated cooling load is 157.47 kilowatts. This relatively large cooling load is expected because untreated outdoor air contains a large amount of heat and moisture. And after cooling, the air is reheated to the required supply temperature. The reheating load is 19.47 kilowatts. Compared with the cooling load, the reheating load is relatively small. Therefore, most of the energy consumed by the system is associated with cooling and dehumidification rather than reheating. To improve energy efficiency, a mixed air strategy is analyzed. Instead of using only outdoor air, the system makes 30% of outdoor air with 70% of conditioned return air. Because the return air is already cooler and drier, the mixed air entering the cooling coil has much better thermodynamic properties, and the mixed air temperatures become 28.07 degrees Celsius. The humidity ratio decreases to 0.0156 kilograms per kilogram. The enthalpy also decreases significantly to 68.01 kilojoules per kilogram. This reduction in enthalpy means the cooling coil receives air containing much less than the thermal energy. As a result, the refrigeration system requires much less energy to cool the air to the desired supply condition. This demonstrates why mixed air systems are widely used in commercial buildings. Next, this slide compares the energy performance of both operating strategies. The 100% fresh air system requires a cooling load of 157.47 kilowatts. In comparison, the mixed air system requires only 60.88 kilowatts. This corresponds to an energy reduction of approximately 61.3%, which is equivalent to about 96.78 kilowatts. Based on these values that present in this slide, and this significant reduction is achieved because the return air has already been cooled and dehumidified before mixing. So consequently, the cooling coil removes much less heat than in the fresh air system. However, there's also an important trade-off. Because the mixed air system recirculates 70% of return air, so the amount of fresh outdoor air entering the building is reduced. Therefore, carbon dioxide concentration and indoor air quality must be monitored using CO2 sensors and proper ventilation control. So when these systems are properly managed, the mixed air strategy provides excellent energy savings while maintaining the occupants' comfort. Next, the slide explains why sensible cooling alone is not sufficient in tropical climates. Because during sensible cooling, only the dry bulb temperature decreases, but the humidity ratio remains constant because no moisture is removed. So as shown in the psychrometric process, simply cooling the outdoor air would still leave it with excessive humidity. As a result, the air would remain outside the ASHRAE comfort zone even if the temperature reached 25 degrees Celsius. So to achieve the desired indoor condition, the air must undergo 3 stages. First, it must cool below the dew point temperature. Second, water vapor condenses on the cooling coil surface, reducing the humidity ratio. And finally, the air is reheated to the required supply temperature before entering the room. Therefore, tropical HVAC systems require both sensible cooling and latent cooling to provide comfortable indoor conditions. In conclusion, the project demonstrates that psychrometric analysis is an effective tool for designing HVAC systems in tropical climate. and the psychometric chart was successfully used to determine the air properties and evaluate the cooling and dehumidification process. And the selected intermediate state of 15 degrees Celsius saturated air provides effective moisture removal while maintaining the safe and efficient cooling coil operations. The comparison between the two systems shows that the mixed air strategy provides much better energy performance than the 100% fresh air system. And although proper monitoring of indoor air quality is required, the mixed air system offers the best balance between thermal comfort, energy efficiency, and sustainable HVAC applications. And therefore, it is the preferred solution for tropical air conditioning applications. That's all for me. Thank you.